Drifting in the silent void between the orbits of Mars and Jupiter is an anomaly. It is a dense, deeply scarred block of solid metal, roughly 140 miles across. This is 16 Psyche. Out of millions of objects in the main asteroid belt, it belongs to an extremely rare class known as M-type asteroids. Scientists believe it is the exposed iron and nickel core of an ancient protoplanet, a world whose rocky outer crust was stripped away by collisions billions of years ago. Because it is essentially a floating planetary core, the concentration of heavy metals is dense. Current estimates place the raw value of Psyche's iron, nickel, and rare minerals at roughly $10,000 quadrillion. That is enough to dwarf the entire global economy of Earth many times over. Utilizing these resources would allow for the expansion of large-scale orbital manufacturing and resource acquisition. But to reach that stage, humanity must first overcome three distinct, massive barriers. Psyche is currently over 230 million miles away. If you try to haul heavy mining equipment across that gap using a traditional chemical rocket, the mission fails before it really begins. A chemical rocket burns through its fuel in minutes, entirely insufficient for the deep solar system. NASA has already taken the first step to bridge this gap. In late 2023, they launched a dedicated scout probe designed to map the asteroid's surface terrain and measure its magnetic field. To survive the journey, the spacecraft relies on solar electric propulsion. Instead of setting liquid fuel on fire, massive solar arrays harvest electricity to ionize xenon gas. It produces a faint blue glow and a very gentle thrust, but can run continuously for years, slowly building up an absolutely incredible speed. Even with continuous thrust, the spacecraft needs help to reach its target. In 2026, it will perform a gravity assist maneuver, diving close to Mars and using the planet's gravitational pull to slingshot outward, increasing its velocity without using extra propellant. It is a grueling, highly calculated 6-year transit across the entire solar system. If orbital mechanics are perfect, the probe will finally enter the asteroid's gravity in August 2029. Successfully arriving at Psyche proves we have the technology to cross the distance. But navigating a probe into orbit only solves the transportation problem. Physically pulling metal out of the rock is a much harder physics equation. On Earth, gravity does most of the heavy lifting for a mining drill, holding the machinery firmly against the ground. On an asteroid, the gravity is practically zero. If you push a drill bit into a solid iron surface, the reciprocal force will simply push your entire spacecraft backward into the void. You cannot land on an asteroid. You have to dock with it. Engineers are developing specialized anchoring harpoons that fire deep into a rock, and magnetic footpads that lock on to the solid metallic surface to hold the extraction equipment firmly in place. Once secured, the metal has to be separated from the rock. Traditional smelting requires vast amounts of water and extreme heat, luxuries you don't have in a vacuum. Instead, carbonyl processing exposes raw asteroid material to carbon monoxide gas, separating out pure iron and nickel. Those gases are then broken down to deposit solid metal layers, essentially 3D printing pure metal components directly in zero gravity. Because Psyche is so far away, radio signals take up to 40 minutes to make a round trip to Earth and back. You simply cannot remote control a robot with a 40-minute lag. The entire extraction, processing, and manufacturing sequence has to be flawlessly executed by self-repairing swarms of autonomous AI. Yet even if AI swarms perform flawlessly and extract the ore, returning thousands of tons of heavy metal to Earth introduces a completely different threat. You might solve the physics, only to accidentally crush the global economy. This is the paradox of abundance. Value is dictated by scarcity. If a corporate mining fleet suddenly flooded the terrestrial market with millions of tons of cheap iron, nickel, and gold, the sudden oversupply would crash global commodity prices instantly. The practical goal is in situ resource utilization. By mining and manufacturing off-world, you bypass the cost of launching heavy steel from Earth's gravity well, providing the raw materials to construct massive orbital stations, solar satellites, and lunar habitats without ever entering an atmosphere. But to fund that infrastructure, you need investors, and investors require legal property rights. Under the 1967 Outer Space Treaty, no nation can claim sovereignty over a celestial body. However, recent domestic laws in the US and Luxembourg state that private companies can own the resources they extract, creating an unresolved legal gray area. This animated graph shows exactly how legal uncertainty destroys corporate funding. We are looking at a simulation tracking the net present value of a 10-year asteroid mining mission. When international laws are ambiguous, the perceived financial risk requires a high discount rate of 25%, causing the mission's value to plummet below zero. But when a stable legal framework is introduced, the line climbs into profitability. Furthermore, if a treaty mandates a 5% revenue share to distribute wealth, the profitability grows slightly slower, but still safely crosses into the green. The math is clear. Without an internationally recognized legal framework that guarantees property rights, the financial risk remains too high, and the physical mining swarms will never leave the launch pad. The iron and nickel found on 16 Psyche provide the structural foundation for a future expansion across the solar system. In 2050, the industrial phase begins, seeing the arrival of large-scale autonomous extraction fleets to the main asteroid belt. The engineering roadmap is already in motion. The ion propulsion systems are proven, and autonomous AI is accelerating at a rapid pace. The primary bottleneck is no longer the physics. It is world governments running out of time to write the laws. Shifting future industrial growth to the vacuum is the only way to meet the resource-heavy needs of a growing civilization without digging further into the Earth. Moving these industries off-planet protects the terrestrial ecosystem while securing a permanent presence in the cosmos.